The Milky Way is a tremendous structure in space containing billions of stars and trillions of planets. In their turn, these objects are surrounded by gigantic clouds of interstellar dust and scorching hot gas streams. All these components make up the bizarre and fascinating picture called galaxy. And today, we invite you on an exciting journey across it. We'll start out near the star system closest to our Sun, Alpha Centauri. Whizzing on hundreds of times faster than light, we will fly around some of the most remarkable stars closest to us, and then briefly stop near an unusual planet whose surface is completely submerged by a perpetually boiling ocean. Placing our lives in peril, we will nevertheless approach an unstable pulsating giant enjoying its last millennia of life, and then pay a visit to the most extreme and forbidding exoplanets. Straight after that, it will be time for the most mysterious and dangerous objects in the Milky Way, black holes. And then we will pierce the galaxy in a swift flight, from the bright center richly illumined by the stars to its very edge, concealing mysterious dark matter. Let's get ready, and we begin. The Earth has been emitting structured radio signals into space for around 100 years now. The radio noise from the Earth reached dozens of other stellar systems long ago, including Arcturus, lying 37 light-years away from us, and Aldebaran, which is roughly 65 light-years away. Besides, our radio signals may be heard on the surfaces of a great number of potentially habitable exoplanets, like Ross 128b or Gliese 667cc. Still, the triple stellar system of Alpha Centauri remains the closest neighbor of the Sun, which automatically makes it the first obvious candidate for the destination of the first ever interstellar flight. Alpha Centauri is known to be a multiple stellar system made up of 3 components. 2 of the larger ones are relatively close to each other. Seen with the naked eye, they appear to be a single source of light. The 2 components follow a slightly elongated orbit around the common mass center, which takes around 80 years to complete. The maximal distance between the stars may reach 35 astronomical units, with the minimal distance reaching 11.2 astronomical units. As for the distance between these objects and the Sun, it is reportedly 4.36 light-years. The most massive, the largest and the brightest component in the system is dubbed Alpha Centauri A. This is a main sequence star with a mass of about 108% that of the Sun. Its radius is reportedly 1.22 times that of our Sun. Even though the surface temperature and the spectral class of Alpha Centauri A are close to those of our star, it emits 1.5 times as much energy. There are no confirmed exoplanets in the environs of this star. However, while the star was being observed in the infrared in 2021, some evidence was found of there being a planet-like object close by. According to preliminary estimates, its mass may be anything from 9 to 35 Earth masses, and its radius may measure 3.3 to 7 times that of our planet. 1.1 astronomical units away from its parent star, the hypothetical celestial body completes a full orbit around it within roughly a year. Additional observations are called for to verify the data, which can be done with the help of either the James Webb Telescope or else Earth-based observatories. The second component of the system is called Alpha Centauri b, or Ptolemy, and it also falls into the class of main sequence stars. However, its mass is 10% less than that of the Sun, and its radius measures only 86% or so that of the Sun. Ptolemy is also slightly cooler than our star. Its surface temperature is reportedly 5,260 Kelvin, or slightly lower than 5,000 degrees Celsius. With these factors combined, the celestial object has an orange hue, and its luminosity is on average twice as low as that of our Sun. Incidentally, Alpha Centauri b emits a lot more energy in the X-ray range compared with other objects of its class. Besides, the star is peculiar for its temper, and there are bright flares and ejections to be seen on its surface. No confirmed exoplanets have been detected near this star either. In 2012, a group of astronomers from the Geneva Observatory put forward a suggestion that there was a planet very close to it, whose orbital period was around 12 days and whose radius measured slightly less than that of the Earth. The suggestion was made based on 4 years of observation of the star's proper motion. However, 3 years later, a mathematical error was detected to have been made in the course of data processing, and so the idea of there being a planet was found to be erroneous. The third component of the system is a stark contrast to the first two. It is a red dwarf with a mass approximately 12% that of the Sun. Its size is about 7 times smaller than that of the Sun. Its surface temperature is only slightly higher than 3000 Kelvin, and its luminosity is just a measly 0.17% that of the Sun. Of all the components of the Alpha Centauri system, it is this dim space object that is the closest one to the Sun, lying 4.25 light-years away from it. This is what earned it its name, Proxima Centauri, which is Latin for closest. Besides, the object is getting nearer and nearer. Thus, in 26,700 years, it will be only a bit more than 3 light-years away. Still, this star cannot be seen from the Earth on account of its low luminosity. Proxima is noticeably far from its two companions in the stellar system. This distance is currently around 13,000 astronomical units or 0.21 light-years, but in the next 300,000 years it is expected to gradually shrink to just 4,100 astronomical units. It takes Proxima 547,000 years to orbit around the system's common mass center. Unlike its two larger neighbors, the Proxima Centauri system boasts 2 confirmed exoplanets, as well as at least one hypothetical object. Besides, studies of the star in the infrared allowed scientists to assume that there is a dust ring and probably a great number of small celestial objects, like asteroids or comets. The first planet in the system, Proxima Centauri b, was detected in 2016 by the radial velocities method. 4 years later, in 2020, it was confirmed by spectrographic studies with the help of the largest Earth-based telescope on our planet, VLT, the Very Large Telescope. According to the updates, the exoplanet lies 0.05 astronomical units away from its parent star, and it takes it roughly 11 Earth days to complete a full orbit. Estimates show that the planet's mass is 10 to 20% bigger than that of the Earth, and its radius measures about 1.3 times that of our planet. Mathematical modeling revealed that Proxima Centauri b gets about 1.5 times as little thermal energy from its star as does the Earth from the Sun. Its average temperature is 234 Kelvin, or 39 degrees Celsius below zero, which means that hypothetically there could be liquid water in some areas on the planet. As the celestial body is extremely close to its host star, however, it is likely to be tidally locked, so it faces the star with one and the same side. A dense atmosphere could compensate for sharp contrasts in temperatures, which are inevitable in such conditions, but just like any other red dwarfs, Proxima Centauri is often seen to eject stellar matter. Also, ionizing radiation flares are observed. It is assumed that such activity gradually destroys the atmosphere of the closest objects. A powerful magnetic field that could be encompassing Proxima Centauri b could offer some protection against the destructive process, but chances that there is any magnetic field there are thin. In the year 2020, another planet was confirmed to exist in the system. A space object dubbed Proxima Centauri c lies roughly 1.5 astronomical units away from the center of the system. Its orbital cycle is slightly over 5 years. As for the object's mass, it may be 6 to 8 times that of the Earth, but its radius hasn't been estimated at the time this video is posted. Depending on its size, meanwhile, the exoplanet will fall either in the category of mini-Neptunes or super-Earths. As Proxima Centauri c lies quite a big distance away from its parent star, its temperature is remarkably low, about 39 Kelvin or 234 degrees Celsius below zero. According to some observations, the planet may have a ring system whose radius is roughly 5 times that of Jupiter. Also, based on the latest data from VLT, a remarkably small exoplanet is expected to lie 0.029 astronomical units away from its parent star, whose mass is about 25% that of the Earth. If it does exist, and if this isn't another measurement error, a year on this planet lasts about 5 Earth days, and the surface temperature there could be 360 Kelvin or 87 degrees Celsius. Whether this space object is really there or not remains an open question, and additional confirmations are called for. Alpha Centauri has been listening to our radio signals for over 100 years now. But the 40 trillion kilometers of space vacuum between us are too overwhelming for us to cover at this point. It takes light over 4 years to get there, but for humans such speeds are still in the realm of fancy. Even today's swiftest state-of-the-art spacecraft would need tens of thousands of years to cover this distance. However, application of advanced technologies could theoretically greatly reduce travel time. Since the very dawn of space exploration, projects of a great number of spacecraft have been suggested that hypothetically would have been able to negotiate interstellar distances. Nevertheless, not a single one of them has been actually designed. Most of these would-be missions were forgotten, but one is still under active consideration. This is the Breakthrough Starshot program, which implies sending as many as 1,000 microprobes to Proxima Centauri as soon as in the first half of this century. They will not measure over a centimeter in size, and special thin and durable sails are planned to be created to aid the probes along. The sails will be blown out, as it were, by impulses of a highly powerful Earth-based laser. Estimates show that an interstellar probe like that is going to be leaving the solar system at a speed roughly 20% that of the speed of light, with the overall travel time around 20 years. After that, it will take another 5 years or so for the data collected by the mission to reach the Earth. By galactic standards, the area of space on the outer edge of the solar system is considered to be sparsely populated by both stars and other space objects. Still, approximately 50 stellar systems are known to be located within the radius of 15 light-years from the Earth. Some of them are single stars, while others contain 2 components and more, which is why the total number of stars in this area reaches 65. Many of them have exoplanets and protoplanetary disks made up of gas and dust, where celestial body formation processes are still in progress. In order to analyze this great variety, we'll have to map out the environs. As we slowly recede from our home planet, we will cover dozens of light-years of space and visit quite a few remote worlds. It is time to set out to the stars. Having traveled 6 light-years away from the Sun, we will reach our first stop, a small red dwarf, designation GJ699, also known as Barnard's star. It is remarkable for its incredible travel speed across the sky, and also for the fact that it's capable of crossing the lunar disk in the course of 180 years. This is due not only to its close proximity to us, but also to its great proper motion. Barnard's star is moving towards the solar system at a speed of slightly over 100 kilometers per second and is going to become our closest star in about 10,000 years. By then, the distance between Barnard's star and our Sun will be just 3.8 light-years. But the red dwarf is so dim that it will not be visible even at such a small distance, and it will be possible to observe it only through optical devices. The star's mass is just 17% that of the Sun, and its radius is 6 times as small as that of our star. Just like all red dwarfs, Barnard's star is quite cool, with a surface temperature just 3,134 Kelvin, or slightly under 2,900 degrees Celsius. With these characteristics taken into account, It isn't surprising that the object's luminosity is 2,300 times lower than that of our parent star. In 2018, the results of a 20-year observation of the star's proper motion were published, which may provide evidence for the presence of an exoplanet nearby. The calculations show it to be a cold super-Earth with a mass of not less than 3.2 times that of the Earth. The planet, named GJ699b, is located about 0.4 astronomical units from the center of the system and takes 233 days to complete a full orbit around its parent star. Unfortunately, the exoplanet follows an orbit that does not lie between the Earth and its parent star, so it's hardly feasible to carry out spectral analysis of the object. Still, mathematical modeling may give us some insights into what it's like. As Barnard's star is very dim, its planetary companion receives 50 times less energy than does the Earth from the Sun. That is why the temperature on the celestial body's surface is extremely low, just 105 Kelvin or 168 degrees Celsius below zero. However, it cannot be ruled out that tidal disturbances or radioactive decay may have released enough energy in the planet's interior to form a warm subsurface ocean. If that is the case, the potential life in its depths would have had ample time to gradually develop. For among the known stars, Barnard's star appears to be one of the oldest. According to estimates, its age is over 10 billion years, which is only a fraction of the expected lifespan of a star. As it is located quite close and is moving in a favorable direction, Barnard's star is one of the highest priority objects for a potential interstellar flight. Time will show if spacecraft launched from Earth will ever reach it. Meanwhile, on the other side of the Sun, there lies the almost exact opposite of the dim red dwarf. Of course, we're talking about Sirius, the brightest star in the night sky, which is 8.6 light-years away from our planet. From Earth, the star appears to be a single light source, but close inspection revealed that it is not a single object, but a binary star. The two components of the system are currently at their maximum distance from each other, about 30 astronomical units. The main star, also called Sirius A, is a bright blue and white star with a mass 2 times that of the Sun. At the same time, it is about 70% larger in diameter, and its surface temperature reaches 10,000 Kelvin. Because of this, Sirius A emits 25 times more energy than our Sun. The second object, known as Sirius B, is barely visible against the background of its bright and massive companion. It is a white dwarf with a radius of about 6,000 kilometers and a mass very close to that of the Sun. Like all stars of this type, its surface temperature is extremely high, reaching 25,000 Kelvin. However, due to its small size, this white dwarf is about 1,000 times dimmer than its stellar companion. After long and persistent research, no signs of planets have been found in the vicinity of Sirius. The reason for this may lie in the comparatively young age of the stellar system, or else the special position of the ecliptic plane. Because of this, the hypothetical exoplanets do not pass between the light source and the Earth, and therefore cannot be detected by the transit method. Another hypothesis claims that Sirius B exhausted its stellar fuel supply roughly 120 million years ago and transformed into a red giant. Soon afterwards, it shed its outer layers, turning into a compact and very hot white dwarf. As a result, the protoplanetary gas and dust disk enveloping the young stellar system at the time was destroyed by this explosion, its remnants scattered into the space around, denying the forming planets any chance of survival. Currently, both components of the system are moving around a common mass center in moderately elongated orbits, completing one every 50 years. Over the next 60,000 years, Sirius will gradually approach Earth, becoming brighter and more visible in the night sky. The minimum distance between us will be about 7.5 light-years, after which the system will start to slowly drift away from us. things will go on like this for about another 660 million years, after which Sirius A will meet the same fate as its companion. For a brief moment, a massive flare will boost its luminosity by a factor of thousands, but within a few months, the star will fade completely, vanishing from the sky forever. Leaving the vicinity of Sirius, permeated by lethal ultraviolet radiation and stellar wind, we will perform a maneuver near the solar system to reach a small star 14 light-years from the Earth. It is designated differently in different catalogues, and one of its names is Wolf 1061. The star is a red dwarf with a radius of about 30% that of the Sun. Its mass is about 4 times smaller than that of our star, and its surface temperature is 3,272 Kelvin, or about 3,000 degrees Celsius. Like all objects in its class, Wolf 1061 is extremely dim. Its luminosity is only 0.14% that of the Sun, so the star is not visible to the naked eye from Earth. However, this red dwarf has one of the most abundant and diverse planetary environments of any stellar system near us. As many as 3 exoplanets have been discovered in its vicinity, all of them rocky and similar in composition to Earth. But still, conditions on each of the 3 celestial bodies differ considerably. The first and closest exoplanet to the parent star is called Wolf 1061b. It is located 0.038 astronomical units from the center of the system and completes a full orbit around it roughly every 5 days. The object has a mass in the range of 1.5 to 2 Earths, and a radius 20% greater than that of our planet. It is likely that the celestial body is tidally locked and faces its star with one side at all times. For this reason, the temperature on the day side of the planet is extremely high, and the flares and stellar winds of the star so close to it virtually rule out any chance of there being an atmosphere. All these factors make the exoplanet completely unsuitable for the genesis and support of life. The second object in the system, Wolf 1061c, is located 0.089 astronomical units from its star and completes a full orbit around it roughly every 18 days. Thus, it is within the habitable zone of the star and can be considered a potentially habitable celestial body. Wolf 1061c is about 3 to 4 times more massive than our planet and belongs to the class of super-Earths. Observations show that its radius is about 1.6 times that of Earth, while the gravity on its surface is calculated to be 60% higher than what we're used to. The exoplanet receives noticeably less energy from its star than the Earth does from the Sun, so its temperature of equilibrium is much lower. It is 223 Kelvin, or about 50 degrees Celsius below zero, which is slightly higher than on Mars. Nevertheless, given variations in temperature during the day and from season to season, liquid water may well exist on the surface of the celestial body. With a dense atmosphere with a pronounced greenhouse effect, this probability is even higher, and conditions on the planet could approach favorable ones. Of all the potentially habitable exoplanets known to date, Wolf 1061c is one of the closest, ranking 5th on the list. The third object in the system is called Wolf 1061d. It follows a clearly elongated orbit, with the distance between the parent star and the aphelium reaching 0.73 astronomical units. As for the perihelion, it lies much closer to the system's center, just 0.21 astronomical units away. It takes the celestial object about 217 Earth days to complete a full year rotation. The mass of Wolf 1061d is calculated to be roughly 7.7 times that of our Earth. If this celestial body turns out to be a rocky object, its radius is supposed to measure about 1.7 times that of the Earth. If, on the other hand, this planet falls in the category of mini-Neptunes with a thick multi-layer atmosphere, its diameter is supposed to be not less than 2.2 times that of our planet. In spite of a comparatively high eccentricity of its orbit, Wolf 1061d never enters its star's habitable zone. The celestial body is likely to be completely unsuitable for supporting life, but may pose a great scientific interest in terms of planetary evolution. This system is one of top priority destinations for future explorations, and it is highly probable that there are new discoveries to be soon made in it. In addition to everything else, the star Wolf 1061 is also remarkable for its position, which is virtually at the very edge of the so-called local interstellar cloud. It is an area in space filled with hot but extremely rarefied hydrogen. Its temperature measures about 7,000 Kelvin, and on average there is just 0.3 of an atom to be found in 1 cubic centimeter of space here. It is about twice as little as the average value in the Milky Way. The solar system has been moving through the local cloud for the past 10,000 years. Its average diameter is about 30 light-years, but our system is almost at its very edge. Alpha Centauri, for example, is already in the neighboring so-called G-cloud. We, on the other hand, will spend about another 2,000 years within our cloud, after which we will enter an even thinner and hotter region. The local interstellar cloud was formed by the collision of two giant bubbles of hot cosmic gas. It has a momentum of its own, which is perpendicular to the direction of the solar system's motion, and also has a magnetic field and radiation. Fortunately, despite the high energy of the interstellar gas particles that make up the cloud, there is no threat to organisms on Earth. The solar wind is a reliable protection against cosmic hydrogen, and the Earth's dense atmosphere takes the hit of particles that do break through the heliosphere. Still, traces of the isotope Iron-60, also called interstellar iron, have been found in the ice of Antarctica. It is thought to have arrived to Earth from no other place but the local interstellar cloud. As we continue our journey through space, we will soon get to a rather unusual star called AP Columbae, located 27.4 light-years away from Earth. First and foremost, it draws our attention because it was born just 40 million years ago, when the dinosaurs would have long since died out on our planet. What is even more striking is that its birth took place in a completely different region of the galaxy, 450 light-years from the object's present position. Young stars usually remain close to their stellar nursery for quite a long period of time, up to several 100 million years. If you analyze the movement of AP Columbae, however, you will find that it probably previously belonged to the open cluster IC2391. The cluster has about 30 stars, united by a common origin and direction of movement. But a few million years ago, one of them exploded, shattering the delicate equilibrium of a multitude of cosmic bodies. This catastrophe gave the young star an additional momentum that swiftly expelled it from its birthplace. A very small red dwarf with a mass just 13% that of the Sun, this star emits 4 times more energy than any other known celestial body with the same parameters. In addition, its radius is twice as large as calculated based on the modern stellar structure theory. Strangely enough, another unusual feature of the star has helped to provide answers to these riddles. According to spectral analysis of its radiation, the stellar matter of AP Columbae contains an abnormally large amount of lithium. Normally, this element is found in abundance in protostellar clumps, but it burns out completely after the start of a thermonuclear reaction. This means that the star is very young and at the very beginning of its formation, not even in the main sequence phase yet. As a consequence, AP Columbae is unstable and explosive in nature. It is prone to violent outbursts and stellar matter ejections, during which its luminosity may increase by up to 10 times for a short while. Such events would normally threaten exoplanets nearby, stripping off their atmosphere and sterilizing their surface with ultraviolet radiation. As it is, observations show that there are no large space objects within 4.5 astronomical units of this star. In all likelihood, it is too young for the formation of fully fledged planets. Nevertheless, it is a unique cosmic body, very important for understanding early evolutionary stages of stars. As we've seen, not every star has a planetary system, so our next stop is near the orange dwarf Gliese 370, 37 light-years from Earth. In 2011, a single exoplanet was discovered near it, designated Gliese 370b. The object was discovered with the use of the radial velocity method and has a mass of 3 to 4 Earths. According to current understanding of the formation of celestial bodies, the discovered world is most likely a rocky planet, with a radius about 30% larger than the Earth's. Under such conditions, the gravity on its surface may be at least 40% higher than what we're used to. Gliese 370b is located at a distance of 0.26 astronomical units from its parent star and completes an annual rotation in 54.4 Earth days. Thus, the exoplanet is in the habitable zone of its star. If the albedo value of its surface is close to that of the Earth, then the average temperature of the celestial body should be about 25 degrees Celsius, which is a few degrees higher than on our Earth. The fact that an exoplanet is located quite far from its parent star suggests that it is not tidally locked and has its own diurnal cycle. This contributes to an evener distribution of heat over the surface of the celestial body, which as a consequence may create a milder climate. A moderately high gravity should smooth out the planet's terrain, which combined with an abundance of liquid water may cause vast seas to form, both warm and shallow. Such places have traditionally been considered the most comfortable for the genesis and support of life. At the time of its discovery, Gliese 370b was considered one of the most favorable exoplanets for potential biological life. However, more recent research has suggested that conditions on its surface are somewhat less attractive than previously thought. In particular, the atmosphere of the celestial body may be too dense and have a pronounced greenhouse effect. Still, even according to the most pessimistic predictions, the average temperature on the surface of the object does not exceed 78 degrees Celsius, which corresponds to a temperature range of about 30 to 100 degrees Celsius. Given that our planet's climate was about the same during the Archean period, Gliese 370b remains a very promising exoplanet for the search for extraterrestrial life, which means that its exploration must continue. If we stop and look around for a while, we will find that we have already traveled more than 50 light-years away from our solar system. There are over 1,000 stars within its radius, most of them single stars. Others are binary stars or even groups of stars. The most striking example is Castor, a complex and surprising system of as many as 6 components. This stellar system is located 50 light-years away from Earth and is visible to the naked eye as a single source of light. As the second brightest object in the constellation Gemini and the 23rd brightest in the night sky in general, Castor has been known to humans since ancient times. As the system has as many as 6 components, it has a rather complex structure. The 2 brightest of these, Castor A and B, are bluish-white Sirius-like stars, each with a red dwarf companion nearby. The distance between the mass centers of these binaries is about 110 astronomical units, and it takes them 445 years to complete a full orbit. About 600 astronomical units from Castor A and B, there is another compact binary system, consisting of a pair of almost identical red dwarfs. Each has a mass of about 0.6 times that of the Sun and has a surface temperature of about 3,900 Kelvin. The 2 stars are so close together that they take less than 20 hours to complete a rotation. They move around the system's common mass center following a very oblong elliptical orbit with an orbital period of about 14,000 years. So far, no confirmed exoplanets have been found in the Castor system. But if they do exist, they're most likely to be located here, near the faintest component of the system. In 2018, for example, astronomers detected variations in the orbital period of Castor C, which implies there may be a brown dwarf nearby, about 49 times more massive than Jupiter. According to calculations, it is located 14 astronomical units from the parent star and completes a full orbit around it every 54 years. It is possible that, like many red dwarfs, Castor C has rocky exoplanets close by. In this case, the skyline of such a hypothetical object must present a truly incredible spectacle. On one side, a considerable part of it is occupied by two crimson stars circling the sky without stopping, while on the other side, the eternal twilight is diffused by the light of a pair of stars, either of them hundreds of times brighter than the Earth's moon. Whether this is actually the case cannot yet be verified at this point. Although the stars we have visited are great distances apart, they are all within a single structure stretching for the total of about 300 light-years. This is called the local bubble and contains not only thousands of stars, but also several large structures, including the local interstellar cloud. The local bubble was formed by successive explosions of several supernovae that occurred between 10 and 15 million years ago. It is a giant cloud of interstellar gas heated to 1 million Kelvin. Because of its high temperature, the gas tends to expand, so its density is about 10 times lower than the galactic average. In addition, the hot ionized hydrogen constantly emits X-rays. Fortunately, the magnetic fields of the Sun and the Earth, as well as the atmosphere of the planet, successfully protect us from the harmful radiation. The local bubble is bordered by other similar formations. For example, slightly away from the direction of the solar system's motion is the so-called Bubble 1, formed by supernova explosions in the vicinity of Antares. This giant cosmic structure has been actively interacting with our bubble for a long time, which has caused the formation of tremendous compactions located at the region at the edge. The center of the neighboring bubble is about 500 light-years from us, and the solar system will reach its margins in a few tens of millions of years. Clouds of scorching hot gas and open clusters, giant nebulae and stellar streams. All these majestic cosmic structures add up to a single system called galaxies. In turn, they combine to form galactic filaments, giant streams and walls stretching for billions of light-years. This forms the large-scale structure of the universe, with countless different stars and worlds lurking in its depths. Who knows what we're eventually to find among them? The first steps in theoretical confirmation of there being ocean worlds out there, that is, planets fully covered in water, were made back in the 1970s. That is when evidence was found that radioactive decay in a planet's interior and tidal forces may cause water ice to melt and subsequently form huge oceans. In all likelihood, similar processes take place on Jupiter's and Saturn's satellites. However, these celestial bodies remain icebound as they lie too far away from the Sun, whose rays would otherwise melt the thick layers of ice. But when we talk about an ocean planet, a slightly different type of space object is meant. The term implies that the ocean on a planet's surface isn't concealed under a layer of ice, and its depth measures more than 100 kilometers. Theoretical calculations of these planets' formation and evolution processes were carried out in 2004 by French astrophysicists headed by Christophe Satin. According to this theory, if the mass of a forming planet is more than 10 times that of the Earth, this starts to actively attract hydrogen and helium from the gas and dust cloud around it. In this manner, with time, it grows into a gas giant. By contrast, if this planet's mass is just 6 to 8 Earth masses, the new planet is going to be comprised of ice and rocks roughly in equal measure. Just to compare, the mass total of all water in the global ocean on our Earth accounts for just 0.025% of the Earth's total mass. In this case, provided a space object's orbit lies far from the host star, this object is going to be either an ice giant or a cold super-Earth. Radioactive decay taking place inside the core will help melt some portion of the ice, which in its turn will help form a subsurface ocean, but the planet's outer layers will still remain frozen. If the planet happens to find itself in its star's habitable zone, its outer layers will melt and spill all over the surface in a boundless ocean. Theoretical calculations show that a planet with a mass 6 to 8 times that of the Earth may have a layer of water over 100 kilometers thick. The pressure exerted by this amount of water may reach 20,000 atmospheres, depending on temperature, impurities and other parameters. This is enough for some special exotic varieties of ice to form, like ones remaining solid even at high temperatures.
I've got home internet from T-Mobile. It only costs $50 at T-Mobile. Just one cord to set up. Say goodbye to that truck.
Home internet from T-Mobile, just $50 a month.
In addition, unlike the familiar water ice, these modifications would be heavier than liquid water. For example, the density of ice 7, which is likely to form in these conditions, should be around 1,650 kilos per cubic meter. This ice settles on the planet's ocean's bottom and forms a massive cryosphere that envelops the more massive core. The opportunity to put these theoretical assumptions to test arose when a tiny and dim star was spotted 42 light-years away from the Earth. It was dubbed Gliese 1214. The diameter of this red dwarf turned out to be 5 times smaller than that of the Sun, with its mass just 15.7% that of the Sun. At the same time, Gliese 1214 is 300 times dimmer than our parent star, while its surface temperature is only 3000 Kelvin, or 2700 degrees Celsius. There is nothing particularly remarkable about the star itself. To be blunt, it is just another nondescript red dwarf that looks like any of the billions of other stars in our galaxy. However, in 2009, a solitary planet was detected in its environs, which was dubbed Gliese 1214b. With its diameter measuring 2.5 times that of the Earth, this exoplanet is just 6.5 times heavier than our home planet. Straightforward calculations show the freefall acceleration on the exoplanet's surface to be just 91% that of the Earth. The average density of Gliese 1214b is approximately 1,870 kilos per cubic meter. Judging by this comparatively small value, the exoplanet cannot realistically be made up of mostly metals and rocks, as is the case with our Earth, for example. But incidentally, this average density value seems to confirm the assumption that the astronomical body is 75% water or water ice and just 25% rocks. Thus, it appears safe to suggest that this exoplanet is an ocean planet. The object lies very close to its host star. The average distance between them measures just around 2 million kilometers, or 0.014 astronomical units, which is 75 times smaller than that between the Earth and the Sun. Also, the orbit eccentricity is rather high at 0.27, slightly more than that of Pluto. This means that in its perihelion, Gliese 1214b is approximately twice as close to its star than when in its aphelion. As for its orbital period, it takes the planet about 36 hours to complete it. The red dwarf Gliese 1214 may be 300 times dimmer than the Sun, but this incredible proximity to the star makes the climate on Gliese 1214b scorching hot. Supposing the reflection coefficient of the surface of Gliese 1214b is the same as that of Venus, the planet's surface temperature is supposed to be around 393 Kelvin or 120 degrees Celsius. If, on the other hand, the surface is darker, the temperature may reach as much as 553 Kelvin or 280 degrees Celsius. Due to the fact that the orbit of Gliese 1214b crosses the star's disk, scientists are able to carry out spectroscopic investigations of its atmosphere. Still, the results are rather ambiguous. If this space object really is an ocean planet, its atmosphere is supposed to predominantly consist of water vapor with some accompanying gases. Interestingly, no lines of hydrogen, helium, or complex substances like water, CO2, and ammonia have so far been detected in the planet's spectrum. It is thought that the outer layer of the dense atmosphere conceals its true content from the observer. The conditions on the surface of Gliese 1214b remind one of what it is like inside a giant steam boiler. Interestingly, the atmospheric pressure in its lower strata should be at least 15 times as high as that of the Earth. As the ocean and the atmosphere are in a state of thermodynamic equilibrium, the border between them is rather blurred. No wonder, as the density of water vapor just above the ocean's surface is practically equal to that of constantly boiling water. As we look deeper at the lower strata of the ocean, the pressure will continue to increase until we reach the depth of 100 kilometers. With the pressure value at this depth, water will be unable to remain in its liquid state even at temperatures this high. And so we will see the bottom made up of dense and heavy ice, whose thickness is estimated to be upwards of 5,000 kilometers. Thus, most water on the planet is concentrated here. Below the cryosphere, there should be the core, made up of rocks and metals. Unfortunately, chances of life evolving on any ocean planet are rather thin, even if the surface temperature happens to be more favorable than on this one. This is so due to the fact that oceans on planets like that are too poor in terms of microelements that are vital for living creatures. Even taking into account meteorites that occasionally bombard the surfaces of these celestial bodies, the chemical diversity is simply not good enough for life to originate here. Still, studying ocean planets poses a great scientific interest. According to NASA's mathematical modeling estimates published in 2020, there may be billions of planets of this type in our galaxy, both cold, harboring an ocean under an ice shell, and warm, like Gliese 1214b. Water is one of the most widespread complex chemical compounds in the universe, and this means that the chances of discovering new ocean planets are quite optimistic. "650 light-years away from the Earth, there lies IRC plus 10-16. A majestic star also known as CW Leonis. Its radius at its pulsation peak may reach 560 times that of the Sun, which is about 2.6 times the distance from the Earth to our parent star. With CW Leonis hypothetically placed in the middle of our system, all the planets as far as Mars would find themselves under its surface, which would even brush the inner boundary of the asteroid belt. Incidentally, the star's mass is not that great, roughly 1.5 to 4 solar masses. Its surface temperature is just 2,300 Kelvin, or about 2,000 degrees Celsius. But due to its impressive dimensions, the star emits on average 8,500 times more energy than our Sun. Like any other red giant, CW Leonis is in its final life stage. Its age hasn't been defined precisely, but it is estimated to be several billion years. It is assumed that in its salad days, CW Leonis was a white-blue star with a mass 3 to 5 times that of the Sun. However, by 1 billion years ago, a great part of the celestial body's hydrogen had burned out and transformed into helium. Slowly settling in the star's center, the helium ousted all the remaining hydrogen and formed a scorching hot core which did not participate in any thermonuclear reactions. This process, typical for all stars whose mass is close to that of the Sun, is the starting point for a star's transformation into a red giant. The star's inner pressure causes it to expand to great proportions, which renders the outer layers more rarefied and unstable. The space object's diameter grows to be dozens of times greater, with its color gradually assuming a blood-red hue. A thermonuclear reaction still takes place in the star's depths, which causes the pressure and temperature of the stellar plasma to increase. At a certain point, this unleashes a chain reaction of nuclear fusion, where helium nuclei are transformed into carbon. This is the so-called helium flash. It is a complex, multi-level physical process that dramatically transforms the star's inner structure. With its core incredibly heating up, its outer layers, on the contrary, cool off and darken. There are currently great amounts of carbon in CW Leonis, but its mass isn't sufficient to hit the next level of nucleosynthesis. As a result, the thermonuclear combustion in the object's interior becomes unstable. The stellar matter gradually cools off and shrinks under the influence of gravitation. This heats up the star's interior again, and the reaction is unleashed with a new force. After receiving a new portion of thermal energy, the stellar matter expands again, and the combustion dies down. It is assumed that this cyclic process underlies the occasional changes of the star's luminosity. CW Leonis has a 649-day pulsation cycle, and with the luminosity at its peak is 11,300 times brighter than the Sun. With the luminosity at its lowest, meanwhile, the object emits 6,250 times more energy than the Sun. At the moment of contraction, the upper layers of stellar matter partly detach themselves from the star. This forms a carbon-oxygen gas nebula that the star is enveloped in. According to some estimates, CW Leonis loses 4 times 10 to the power of 22 tons of material every year on account of this process, and amount approximately 7 times the mass of the Earth. Observations show that the circumstellar nebula is not less than 69,000 years old, and its mass is about 1.5 times that of the Sun. As for its size, it reaches 84,000 astronomical units. The nebula has an elaborate structure with bulges and pockets of gas, as well as half-arcs and irregular rings. It is posited that these formations appeared due to magnetic activity and stellar wind generated by the unstable star close by. The chemical composition of the cloud CW Leonis is shrouded in is of great interest to explorers. Spectral analysis data reveals it to contain around 70 different chemical compounds, for example carbon dioxide, water and ammonia, to name but a few. There are also quite a lot of elements from the upper part of Mendeleev's periodic table, right down to iron. CW Leonis may have had planets in the past, but they appear to have been swallowed up early on at the stage of expansion. In any event, years of observations did not reveal distinct traces of their existence in the past. What was registered was subtle changes in the star's orbit back in 1994, and more recently, in 2017, mysterious shifts of matter were detected in the cloud of gas and dust enveloping the star. Some small red dwarf orbiting the giant could well account for these phenomena, although attempts to detect its radiation have so far been unsuccessful. This could be due to the nebula close by, which disperses and reflects the energy flow from sources of light located nearby. This phenomenon camouflages any objects in the immediate environs and prevents them from being accurately recognized. The mass of CW Leonis's hypothetical stellar companion is assumed to be definitely smaller than that of the Sun, and it should take it approximately 100 years to complete a full orbit around the giant. Another outstanding feature is a comparatively high water content in the star's environs and envelope. At first, it was posited that the star would melt and swallow up icy comets as it expanded. However, observations carried out in 2009 showed the temperature of some spectral lines to reach 1000 Kelvin, which is possible only on condition that water vapor forms actually in the upper layers of the giant. This fact did not fit in the model of red giant's structure accepted at the time, according to which all oxygen in stellar matter necessary for water synthesis must be used up completely to produce carbon monoxide. A new hypothesis was put forward to account for the witnessed phenomena, which stated that molecules of silicon oxides and carbon are destroyed by a powerful ultraviolet radiation. After that, the released oxygen reacts with hydrogen and there forms scorching hot water vapor. The weakness of this hypothesis is in the failure to account for the source of ultraviolet radiation. Reactions like that may occur only in rather high temperatures, that is, within stellar matter. However, it is practically impervious to cosmic rays. This paradox may be explained by yet another assumption. Since the star is unstable, large ruptures and low-density areas occasionally occur on its surface, where ultraviolet radiation is not blocked out that effectively. The water vapor's overall mass in the star's atmosphere and outer layers is estimated at several quintillion tons. Enormous though this figure may seem, in fact, water accounts for just around a billionth of the star's overall mass. According to today's notions of stellar evolution, being a red giant, CW Leonis is in its autumn years now. It will deplete its stellar fuel in the next 10 to 30,000 years, after which it will discard its outer layers following a powerful explosion. It will transform into an incredibly hot and dense space object, a white dwarf. Its mass will be roughly 80% that of the Sun, and its temperature will reach several million degrees in the first seconds after the transformation. However, with no energy source, it is destined to slowly and irrevocably fade in the course of billions of years to follow. Eventually, the celestial body will be almost invisible against the background of cosmic emptiness when it becomes a mysterious black dwarf. But this will not happen anytime soon. The shockwave and the mind-boggling temperature in the epicenter will generate new elements that are not to be found in a star's interior. For example, uranium, gold and lead. They will later become part of new celestial objects. Millions of years later yet, radioactive decay will heat the planet's interiors, melt the ice, and saturate the oceans with microelements, thus creating conditions for the genesis of life. The universe is constantly evolving, and global cataclysms and destruction are an inalienable part of this process. But at the end of every storm, there are fresh rays of light. Earlier, in one of our previous videos, we have already taken a look at some terrifying and lethally dangerous worlds discovered in the vast expanses of space. With some of them extremely hot, others are located close to insanely powerful sources of radiation, and yet other ones are peculiar for some bizarre features on their surfaces. However, we haven't quite exhausted our list of the most horrifying planets, and now it's time to see some more. Our first stop is 202 light-years away from the Earth, destination K2-141, an orange dwarf. Its mass is roughly 0.7 that of the Sun, and its radius measures 68% that of our host star. With these parameters almost perfectly proportional, the star's temperature reaches 4,600 Kelvin, which is about 20% less than that of the Sun. And now to the planet in question. Just 0.007 astronomical units away from its star, there lies a really bizarre world, designation K2-141b. This rocky exoplanet is 5 times as massive as the Earth, with its radius 1.5 times as big as that of our Earth. All this gives us grounds to assume that the gravity on the planet's surface is at least twice as strong as that on our planet. The heavy metallic core, meanwhile, accounts for 20 to 50% of the planet's overall mass. It takes the celestial body about 6.5 hours to complete a full orbit around its parent star. Being extremely close, it is tidally locked to it. That is, it faces the star with one and the same side at all times. observations show that the temperature on the planet's day side reaches 3,270 Kelvin or 3,000 degrees Celsius. This is enough not only to melt most rocks and metals, but also to effectively evaporate them. The day side of the planet is assumed to be covered with a lava ocean that never ceases to boil. The atmosphere is thought to be rather exotic, made up of steams of heavy metals and silicates. By contrast, the planet's night side is incredibly freezing. According to estimates, the temperature of most of its area is tens of times lower than that on the day side, and on balance, its values are supposed to be sub-zero. Mathematical modeling shows that this sharp temperature contrast gives rise to exceptionally strong winds whose speed reaches 1.75 kilometers per second. This is roughly 5 times the speed of sound, which means that the surface of K2-141b is continuously shaken by exceptionally powerful, deafening rumbling. It is assumed that on reaching the night side, atmospheric streams condense and precipitate on its surface in the form of fiery rain. This forms lava rivers, and eventually this molten metal makes its way back into a magma ocean to evaporate again later on and to continue this incredible fiery circulation. However, this infernal cycle affects only a relatively small part of the planet's night side. The thing is that masses of evaporated elements from the day side simply don't make it to the main part of the night side and precipitate somewhere on the border. That is why the central part of the night side is likely to be a freezing desert bound with layers of solid rocks. Remarkably, K2-141b is far from being the hottest planet that we know of. For example, there is an object referred to as Kelt 9b lying 670 light-years away from the Earth. Its surface is as hot as 4,600 Kelvin, which is approximately 4,330 degrees Celsius. Just to compare, the outer layers of almost all red dwarfs, for example, are much cooler, which means that in terms of temperature, this exoplanet is quite a match to stars. Its parent star, designation Kelt 9, is of a whitish-blue color and has a mass 2.6 times that of the Sun. As for its diameter, it is 2.3 times that of our star. The surface temperature of Kelt 9 is rather high at approximately 10,170 Kelvin or a staggering 9,900 degrees Celsius. This largely accounts for the extreme conditions on Kelt 9b, which lies quite close by. Just 0.035 astronomical units away from its parent star, the planet completes a full orbit around its system's center roughly every 1.5 days. Kelt 9b is a hot gas giant. Compared to Jupiter, its mass is 2.8 times as big, and its radius measures roughly twice as much as that of the largest planet in our system. Based on today's notions about the composition of this type of planets, the inner part of Kelt 9b's atmosphere is supposed to be even hotter. Estimates allow for this value to reach as much as 11,000 Kelvin on account of heavy metal ionization. With this figure so exceptionally big, it appears that the planet's atmosphere should contain vaporized iron and titanium, alongside the elements we're used to in an atmosphere's composition, such as hydrogen or helium. Its close proximity to the parent star and the extremely high temperature cause the planet to gradually lose its atmosphere. By and by, powerful stellar wind blows it off into space, which is why the object is shrouded in a cloud of rarefied gas. This material will eventually be attracted and absorbed by the star. Interestingly, according to some estimates, the exoplanet loses up to 68 Earth masses every billion years. Theoretically, in a long while, Kelt 9b may well get stripped of all of its atmosphere and transform itself into a Chthonian planet. However, its parent star is likely to hit the final stage of its life cycle long before that, swallowing up and destroying all the celestial objects within its reach. The space objects we have just looked at are a living proof, as it were, of the fact that stars can destroy the planets close to them and not just warm them up. But incidentally, there are celestial objects out there in the universe that have experienced their parent star's wrath in full measure. One of such objects lies 4,570 light-years away from the Earth in the environs of a small star, designation V391 Pegasi. Now, the star is a white dwarf whose mass is twice as little as that of the Sun and whose radius is approximately 23% that of our parent star. The temperature of this celestial object is unbelievably high, at almost 30,000 Kelvin. All thermonuclear reactions in its interior would have run their course a long while ago. Up ahead are hundreds of billions of years of slow cooling, with the white dwarf eventually transforming into a black one. The planet we will look at, referred to as V391 Pegasi b, is in this ordinary star's environs. Its lot is exceptionally amazing. According to mathematical modeling, the planet not only survived its progenitor star shedding its outer layers, but actually found itself almost within the star for some time. It is assumed that when the system's star V391 Pegasi transformed into a red giant, its outer layers, extremely rarefied by then, were almost brushing the planet's orbit. Their density became dozens of times lower than the atmospheric air we're used to, which means that the celestial objects devoured by the dying star remained whole for a while and didn't get destroyed at once. It goes without saying that they would have been losing their speed and dropped into the star's hotter and denser layers. Still, V391 Pegasi shed its outer layers sooner than V391 Pegasi b melted and ceased to exist as a whole object. At the moment, the exoplanet appears to be a gas giant, 3 times as massive as Jupiter. Its orbit passes 1.7 astronomical units away from its parent star, and it takes the planet approximately 1,170 Earth days to complete a full orbit around its system center. It is still not entirely clear how this astronomical body managed to preserve such a big mass after its collision with the scorching hot layers of the star. Their influence was supposed to have destroyed the object's atmosphere completely. However, there is no doubt that the host star's collapse brought about some dramatic changes, both in terms of the exoplanet's orbit and its parameters. That is why it is hardly possible for us to ever find out what V391 Pegasi b was like before immersing in a sea of raging plasma. Space expanses conceal uncountable astronomical objects with the most bizarre properties. Some of them are almost totally invisible through regular telescopes, but can be detected by looking at radio wavelengths when exploring space. An example of such like celestial objects is pulsars, neutron stars spinning on their axes at a mind-boggling speed. These object spectra are peculiar for exceptionally fast and regular pulsations. That is why it is quite easy to detect another celestial body transiting between a radiation source like that and an observer on the Earth. This is precisely the way our next object of interest was discovered. But first we'll be looking at a pulsar which lies around 4,000 light-years away from the Earth. This neutron star boasts quite a long name. Here it is on the screen. And now let's check out its remarkable features. The pulsar's diameter is just a measly 20 kilometers, and its mass is approximately 1.4 that of the Sun. The object spins at an incredible rate, with roughly 10,000 rotations a minute, while continuously emitting powerful electromagnetic radiation impulses. Now the surface of the exoplanet, our next object of interest, is continuously exposed to these waves of lethal radiation, which makes it a hostile and forbidding place. It takes this planet just 2 hours to complete a full orbit around its system's center, and the distance to the pulsar is smaller than the Sun's radius, just 600,000 kilometers or 0.004 astronomical units. Incidentally, the celestial body's surface is bound by eternal cold and space as its parent star just barely emits thermal energy. The object's mass is around 330 that of the Earth, while its radius is 4 times that of our planet. This makes gravity on its surface as much as 20 times stronger than on the Earth. Estimates show the planet's average density to be about 23 grams per cubic centimeter, which is more than most chemical compounds we know. The planet is thought to be made up for the most part of crystallized carbon under a lot of pressure. Besides, the object's upper layers contain some oxygen, which is probably chemically bound with carbon. It is highly doubtful that a celestial body located so close to a star could possibly have survived a supernova event. It is more realistic to assume that the exoplanet formed after the progenitor star had come to the end of its life cycle and had transformed itself into a pulsar. The exoplanet could be a piece of debris left over from a white dwarf whose material would have dispersed for the most part. This makes classifying the exoplanet an especially difficult task. Still, whatever it is, this world remains one of the most dangerous and hostile ones lurking in the depths of the cosmos. It goes without saying that to detect a celestial object that absorbs all light shed on it is a challenging task, to say the least. That is why there are not that many confirmed black hole candidates today. Still, mathematical modeling shows that their number in our galaxy may reach 100 million. This may seem an incredibly big number, but since there are 200 to 400 billion stars in the Milky Way, it makes us realize that in all these expanses, black holes are objects one doesn't come across that much. In one of our previous videos on the topic, we mentioned that a star, the progenitor of a black hole, has to have a mass of at least 18 to 20 solar masses. Only this will ensure a powerful enough supernova to compress the scorching hot core of the star to an exceptionally dense clump of material. After this has occurred, nothing will be able to stand up to the object's gravity force and escape beyond the boundaries of a conventional sphere predefined by the so-called Schwarzschild radius. What used to be a star transforms into a bizarre object with an inner makeup that would defy description by the physical laws we're familiar with. The object, referred to as A0620-00 or V616, is one of the black holes closest to our Earth that we know of. It lies 3,300 light-years away from our planet and forms part of a binary star in the constellation Monoceros. The other object in the system is an orange dwarf with a mass half that of the Sun. Every 7.75 hours, it completes a full orbit around an invisible object of unknown nature. Estimates show the mass of this invisible object to be around 6.6 times that of the Sun. It is admittedly too much for a neutron star. This leads one to believe that the bizarre invisible object is more likely than not a black hole. In addition to getting deformed and elongated by the more massive neighbor's gravity, the orange dwarf is also getting stripped of the outer layers of stellar matter. Spiraling streams of scorching gas gradually flow to the black hole and form a bright accretion disk. It is thanks to this dazzling disk that the black hole was detected. There are at least several dozen stars in the environs of V616, some of which almost certainly have their own planetary systems. It is highly likely that in the future, one of these stars will get dangerously close to the black hole and as a result will be sucked in by the object's insane gravity. This unfortunate star will have no choice, and in this case, the same slow demise is eventually awaiting the black hole's new companion as that of its current one. The process of interaction of a black hole with other objects largely depends on their mass ratio. The smaller the distance between them and the more massive the black hole, the stronger the influence of its tidal forces over its companion. The star may be deformed by them and get stretched towards the system's common mass center. They can also form channels that would carry stellar matter closer to the black hole, adding up to its accretion disk. If the tidal forces happen to be strong enough, they may well destroy the object that is being sucked in by turning it into a fiery ring. It is assumed that there may be planets orbiting a black hole, just as if it were a regular star. In contrast to a widespread opinion, black holes are actually not able to suck in all objects around them indiscriminately. From the point of view of gravitation, In astronomical terms, they behave just like any star with the same mass. That is why, incredibly though it may seem, a black hole may well have a stable planetary system. There are several ways for them to form. Firstly, new celestial objects may originate in a nebula of gas and dust that is formed after a supernova. Influenced by gravitation, they first form clumps of material that collide with each other and attract cosmic dust. As a result, they eventually turn into planets and satellites, as well as large numbers of small celestial objects, like asteroids and comets. The radiation of the black hole's accretion disk may be powerful enough to warm them, and even melt ice on their surfaces. Hypothetically, a planetary system like that could be favorable enough for life to originate and, with any luck, evolve. Secondly, when a black hole captures and destroys another planetary system, some of its objects may choose to take up stable orbital positions around their new host. Of course, this makeover would bring about dramatic changes on the celestial object's surfaces. Thus, an ice giant may transform into an ocean planet, and a gas giant may lose almost all of its hydrogen and turn into a Chthonian planet. Thirdly, space wanderers like rogue planets or interstellar asteroids may also be ensnared by the massive object's gravity. Even though systems like that have not yet been discovered in practice, there is no reason to suppose they are non-existent. If, on the other hand, a planet is too close to the system's center, and the black hole is massive enough, other factors come into play. A scorching hot stream of material forming the accretion disk will strip the celestial object of its atmosphere, and its friction will slow it down and pull it still closer to the black hole. Eventually, extremely powerful tidal forces will rip the planet to tiny shreds. The debris will be pulled into the accretion disk and gradually melt in the hot gas around. In the end, they will inevitably get swallowed up by the black hole and, in essence, become part of it. It is posited that there are three main types of black holes to be found in the universe that are different first and foremost in terms of their mass. The first type can be found in the center of most spiral galaxies. These are gargantuan black holes with masses reaching several billion solar masses. The density of matter in the central part of a galaxy is generally extremely high, which is the reason why there originate a big number of large and bright stars quite closely packed. As they rapidly burn out, they transform into black holes, which in their turn rapidly grow and often merge with each other. As a result, supermassive objects are born, which are surrounded with giant accretion disks made of scorching hot material. They illumine space so brightly that it makes them seen from billions of light years away, even if their galaxy is completely unobservable to us. These objects are known as quasars. The second type is much more widespread, but at the same time, black holes like these are not that easily detectable. Their masses are close to those of stars, and they form out of large stars at the end of the latter's life cycle. By devouring other celestial bodies and interstellar gas, these objects gradually gain in size and eventually turn into intermediate mass black holes. They can also merge together, which generates gravity waves that distort space many light years around. The third type is the hypothetical primary black holes. Their existence has been inferred from today's theory of universe's origins and evolution. Fluctuations in matter that filled space in its early stages of evolution may have been favorable for black holes of infinitely small size to originate. It should be mentioned that according to estimates, the smaller an object of this type, the faster it evaporates, and at the end of its life cycle it turns into a tremendously powerful electromagnetic impulse. Modeling shows that primary black holes with masses around 10 to the power of 12 kilograms are supposed to be flaring up sometime around now, but to date, no such event has been registered yet. According to a certain hypothesis, a microscopic black hole may form on collision of extra high-energy elementary particles. This variety is referred to as quantum black holes. Still, the conditions necessary for such an event to happen are impossible to be reproduced in lab conditions, and estimated life expectancy of these hypothetical objects is so small that it can hardly be measured with today's latest and most advanced methods. That is why quantum black holes still officially exist only in theory. Of course, it is extremely difficult to detect such dark and compact objects. Some of them happen to have a star companion, whose anomalous trajectory of movement gives telltale prompts of there being an invisible thing in close proximity. Another popular method of detection is observation of accretion disks. These object spectra have some typical features that allow telling them from other sources of light in space. Sometimes we're lucky enough to get a snapshot of a disk with a black spot in it that is evidence that the observed object's structure is quite unusual. A black hole may also be detected thanks to the gravitational microlensing effect. This involves detecting the massive invisible object as it transits between the Earth and a remote star. This changes the star's spectrum in a special way. But admittedly, this method requires a number of rare factors to successfully work. There is hardly any doubt that space is filled with great numbers of objects that are dark and not easily noticeable. There may be wandering black holes among them. These mysterious objects, roaming around in interstellar space and absorbing every bit of light they come across, will probably never reveal their secrets to us. Long before telescopes had been invented, people could observe a light strip crossing the heavens. The fascinating and mysterious phenomenon prompted a multitude of legends, but it took thousands of years of scientific progress to finally account for it. It turned out that the Milky Way wasn't a path of gods. What it is the dissipated light of billions of stars too remote to distinguish each one separately. The idea of the stars around us making up part of a single structure of enormous dimensions was first suggested by Immanuel Kant back in 1755. He also assumed that some nebulae discovered by scientists could in fact be remote star clusters, that is, other galaxies. This ingenious guess was well ahead of its time, with the philosopher's contemporaries initially dismissing it. Only in the early 20th century did the progress of observation equipment enable scientists to confirm the existence of other galaxies, and in 1936, Edwin Hubble devised a classification system. Many of its principles are still referred to by scientists today. According to the system, the Milky Way falls into the category of barred spiral galaxies, although it took a long while before it had assumed its today's looks. Our galaxy is quite an old one, since the stars in its central globular clusters were born as far back as around 13 billion years ago. At the same time, there are some areas in the Milky Way where stars are actively born, which means that there is always a fresh supply of young stars. The collected data points to the fact that the Milky Way is a comparatively large galaxy in astronomical terms. The diameter of its disk measures as much as 200,000 light-years, with a halo reaching out into space much deeper yet. Our galaxy is home to at least 200 billion various stars, as well as 25 to 100 billion brown dwarfs. In addition, it contains over 1 trillion planets, countless small celestial objects, as well as clouds of cosmic dust and interstellar gas, which may reach gigantic dimensions. At the same time, regular matter accounts for a small ratio in the galaxy. Around 90% of the Milky Way's overall mass is the so-called dark matter. The amount of light emitted by this mysterious and widespread substance is negligible. However, dark matter plays an active role in gravitational interaction. Even though most of the galactic mass remains invisible, we can still calculate it. To that end, scientists refer to stars' trajectories of movement around the center of the Milky Way. According to the estimates, the overall mass of our galaxy reaches 0.8 to 1.5 trillion solar masses. The structure of the Milky Way is quite elaborate. we'll start our journey today from its center. This area of the galaxy is shrouded in massive clouds of gas and dust, but by happy chance we can observe it through the so-called Bardes window, an area of space with lower amounts of dust. Just like most spiral galaxies, the Milky Way has a supermassive black hole in its center, which is surrounded with an accretion disk with a radius roughly 3 light-years. Dubbed Sagittarius A star, it is the closest object of this class to us. Its mass is 4.3 million solar masses, and its radius isn't over 16 million kilometers, which is 3 times smaller than Mercury's orbit. The first data about the nature of the object in the center of our galaxy was acquired in the course of long observations and thorough calculations. Only as recently as on May 12, 2022, was it possible to get the first image with the help of the EHT network of radio telescopes, and so the earlier hypotheses were confirmed. The area in the center of our galaxy is highly populated. More than 6,000 stars have already been detected within 3 light-years from the black hole, with the orbits of some of them defined rather accurately. For example, there is a white-blue star, designation S62, which is 17.8 astronomical units away from the black hole on its closest approach to it, while moving at 6.7% the speed of light. Classical mechanics laws are inadequate for description of the trajectory of movement of a star as swift as that because of relativistic effects. Just to illustrate, the axis of its orbit shifts by 75 angular minutes with every completed orbit. Besides, when crossing this area in space, we can see several large star clusters with a total mass of around 1 million solar masses. And slightly further, roughly 200 light-years away, another massive black hole is likely to be lurking, whose mass should be around 100,000 times that of the Sun. Traveling further on, we will reach the central molecular cloud, an irregularly shaped area measuring 1600 to 1900 light-years, whose mass is over 60 million solar masses. There are a great many stellar nurseries and gas nebulae, as well as protostars and remnants of supernovae. Most of the cloud's matter is dense hydrogen, whose temperature fluctuates between 50 and 600 Kelvin, which corresponds to 223 degrees Celsius below zero to 327 degrees Celsius above zero. Spectral analysis shows the gigantic nebula to contain carbon monoxide, methyl alcohol, and hydrocyanic acid in addition to hydrogen. Having receded from the Milky Way's center a bit, we will see that it is encompassed by a bulge, a bright and massive formation of an elliptical shape. With its length reaching 10,000 light-years, its transverse diameter is roughly 7 light-years. The total mass of the bulge is as much as 10 billion times that of the Sun. The exact number of the stars cannot be calculated, because their radiation blends and renders any estimates unrealistic. Being elongated, the bulge forms the so-called bar, stretching for approximately 13,000 light-years and serving as the base for spiral galactic arms. It is here, at one of its ends, that we can see the star cluster Stephenson 2, containing the largest known star today. Its designation is Stephenson 2-18, and its radius is 2,150 times that of the Sun. Unfortunately, chances of finding exoplanets orbiting this outstanding object are quite minuscule. Even if planets did exist at some point in the past, the hypergiant would have swallowed them up while it was expanding. The galaxy's center is home to billions of stars and apparently a great number of exoplanets. Chances of encountering a potentially habitable world among this great multitude are much lower than in less populated areas of the galaxy. This is due to the fact that when a big number of stars are located close together, they destabilize exoplanets' orbits, while their powerful radiation is lethal to all living things. That is why a special area in the galaxy is defined as the habitable zone. It looks like a ring, with a radius measuring 22 to 29,000 light-years, and contains star systems with the most favorable conditions for the genesis of biological life. Worlds encompassed by the ring languish in exposure to excessive radiation, while beyond the ring there's a lack of heavy elements. However, mathematical modeling shows that stars within galaxies are able to migrate thousands of light years away, thus either leaving the habitable zone or entering it. Consequently, with an exoplanet lying within the zone, it does not automatically suggest favorable conditions on it. Moving on away from the center of the Milky Way, we will have a chance to check out its most impressive part, the galactic disk. It is made up of two components with different properties. The first one, known as the thin disk, measures 1,000 to 1,300 light-years in thickness, and its visible radius measures as much as 50,000 light-years. On the edge, it gradually dissipates, with the outermost stars lying up to 100,000 light-years away from the galaxy's center. This part of the Milky Way contains around 80% of the galaxy's visible mass, and in fact, it was the last component to have formed. As for the thick disk, its diameter is comparable to that of the thin disk, but it's 4 times as thick and is much more rarefied. It is made up of old stars and is practically devoid of interstellar gas. Observations of some stars in the Milky Way, as well as mathematical modeling, show our galaxy to have swallowed up another one in the period from 11 to 8 billion years ago. This hypothetical cosmic structure was dubbed Gaia Enceladus. It is thought that it contributed several billion stars to the Milky Way, as well as great amounts of interstellar gas and dark matter. It is thanks to this tremendous event that most of our galaxy's thick disk formed, and an additional supply of gas led to a stellar baby boom. There is no doubt that spiral arms are the most noticeable structural elements of our galaxy's disk. Usually 2 major ones are singled out, the Scutum Centaurus arm and the Perseus arm, and 2 minor ones, the Norma arm and the Carina Sagittarius arm. Sometimes a 5th large arm is taken into account, named after the Cygnus constellation. Galactic arms are areas of especially high star count. Most of interstellar gas is also concentrated here, which is why the rate of star formation in the arms is 3 to 5 times higher than in the galaxy on average. They spend the first millions of their lives in open clusters, but gravity forces are too weak to hold the stars close together for a long time. This destabilizes the clusters, and young stars gradually drift away from each other. Traveling along the Carina Sagittarius arm, we will reach a fork that links it to the Perseus arm. The length of this stellar structure reaches 11,000 light-years, and its width measures roughly 3,500 light-years. It is referred to as the Orion arm, and it is here, 27,000 light-years away from the galaxy's center, that the solar system is located. From our planet's perspective, the galaxy's center is seen as a dark abyss. This is the Great Rift, an area of space that shuts out the greater part of the Milky Way from our gaze. It is filled with massive clouds of interstellar gas and dust, and its total mass is as much as 1,000,000 times that of the Sun. Even though the Great Rift is practically not transparent in the optical range, its matter actively emits radio waves and thermal energy. Spectral analysis data reveals that the clouds are mostly made up of hydrogen with a small percentage of more complex compounds, ammonia, alcohols, and amino acids. The Great Rift is thought to be a potential stellar nursery, but it is going to take a while until the first stars light up in that area. While it is still not quite active, let's move on, beyond the galaxy disk. Even though its bright and clearly defined arms attract a lot of attention, there is more to the Milky Way than that. If we look closer, we will see the vastest and the most rarefied of its components, the halo. Its visible part, spherical in shape, stretches for up to 260,000 light-years away from the galaxy's center, but accounts for just a few % of the total mass. The halo contains a great number of globular clusters made up of remarkably old stars over 12 billion years of age and several tremendous stellar streams. The Sagittarius stream, for example, made up of several thousand stars, encompasses our galaxy in an elongated ellipsis, which is almost perpendicular to the main plane. Modeling shows that all these stars are highly likely to have been gravitationally captured by the Milky Way from a dwarf satellite galaxy, designation Sagittarius DEG. It lies 500,000 light-years away from the Milky Way's center and is going to be swallowed up by it completely within several billion years. Another dwarf galaxy has already met a similar fate. Lying in the Canis Major constellation, it was almost destroyed by the Milky Way, which pulled out millions of its stars by gravity forces. Stretching for 200,000 light-years and mixing with other stars, this string of stars with a total mass of roughly 100 million solar masses has already wrapped around our galaxy 3 times. Apart from bright but rare stars and clusters, the halo contains great amounts of gas, whose temperature reaches millions of Kelvin. Also, great amounts of dark matter are thought to be scattered in the vicinity of the Milky Way, forming the so-called dark halo. Stretching for up to 2 million light-years, it hardly emits any electromagnetic radiation and can be detected only by gravitational interaction. The dark halo remains an unsolved mystery, yet it greatly contributes to the global stability of our galaxy. The diversity of space objects is truly fascinating. With some of them spread all over the place, others are absolutely unique. Every corner in space harbors countless mysteries, and whenever some of them are solved, they add to our knowledge about the universe around us. Are we to solve all its mysteries someday? Time will show.